had replaced CNC milled graphite flash in FCDI. Yeah.
Okay, thank you. Good morning. So I'm Sylwin Pawnlowski. You are almost correct. And I'm from Laboratory of Membrane Processes at Nova University of Lisbon, Portugal. And we are working at an European Union project called Circular Mine, which focus on the recovery of critical raw materials such as magnesium, lithium, trace elements from natural and industrial brines. And our task in this project is to recover lithium. So in order to do it, we proposed this new concept of lithium membrane flow capacity ionization, which basically is an FCDI stack with lithium selective membranes incorporated into it. And despite of our feed brine to be a sodium-rich brine, so with much higher quantity of sodium than lithium, actually we were able to achieve some very interesting results and very good selectivity values and to recover successfully the lithium. I'm not going to explain this much more because our PhD student already presented this part of the work on Monday. But as in any FCDI-based process, one of the key elements of this technology are those current collectors and channels for the flow of flow electrodes. And usually they are prepared by CNC milling and in graphite plates. However, when we started this project, actually the COVID pandemic also arrived to Europe and to Portugal, and basically everything was closed down and we didn't have access at this point to CNC milling or to a possibility to buy graphite plate. So in order to move forward with the project, we started to look at alternatives, and one of them was what we studied was 3D printing, which is basically an additive manufacturing technology. It is a part of the fourth industrial revolution, and it's basically it's very simple, very available method, and basically it consists on preparing your objects, to build what you want to create by depositing your material layer by layer, following the commands from the computer, the commands which you create before in, for example, in AutoCAD or SolidWorks. So it's something very simple. And what we did, we had in our lab some electrodialysis stacks. So we used the end plates from those electrodialysis stacks, which has this titanium platinized electrodes, which we use as current collectors. And we printed several different gaskets using the 3D printer and PETG filaments. So these are a non-conductive material. So we printed those gaskets. In the end, we always use this serpentine horizontal arrangement, and we compared the performance of electrodialysis with FCDI with those 3D printed PETG gaskets. And we performed the experiment exactly at the same conditions. The only difference was that in FCDI mode, we use flow electrodes. In electrodialysis, we use sodium chloride solution as electrode rinse solution. And as you can see here in the results, the FCDI clearly outperformed the performance of electrodialysis. The current values were much higher. Here you can see that the conductivity of the diluted stream was much lower for FCDI than for electrodialysis, and obviously it means higher desalination rate and higher salt removal. So the first impression was that, okay, it works. We can use a 3D printed gasket instead of graphite current collectors. But obviously, the correct benchmarking would always to be compared with graphite graphite current collector. So finally, we managed to produce our graphite current collectors. But meanwhile, we also 3D printed a conductive gasket made of PLA, polylactic acid, and carbon black. So the filament which we used to 3D printing was a mixture of these two things, and the carbon black basically add the conductivity to our material. And we did a comparison now only in FCDI mode. We performed a new experiment, a desalination experiment with 3 stacks, with non-conductive space gasket, with conductive gasket, and with graphite current collector. And these are the results. So here in the upper row, you can see the curves of current for non-conductive gaskets, conductive gaskets, and graphite current collector. So you can see that it slightly increased, but this increase of a current is actually not so high. So it means that both 3D printed gaskets actually performed well. And if you look here at the conductivity curves, but we have 2 different situations. For carbon content in the flow electrode of 15%, it follows the expected order. So you have a higher desalination degree for graphite, and then it decreases regarding to conductive and non-conductive. It is expected and logical. For the 5% and also for the 10% of weight percent of the carbon in the flow electrode, actually the conductive gaskets even performed better than the graphite current collectors. And we think that it's because when we printed the 3D gaskets, they are never completely flat. There are some rugosities on the surface of a 3D printed gasket, and we believe that this can add some mixing to create some mixing of the flow electrodes. And also it was mentioned in the previous presentation, basically, when you increase the carbon content of in the flow electrodes, the viscosity dramatically increased. So with 15% or 20%, and we saw it by CFD simulation, there is no chance of having a mixing of a flow electrode. It's fully laminar flow. But with 5 and 10%, you can create some mixing of the flow electrode. And we believe that this rugosity on the surface of a 3D printed gasket add that mixing. And therefore, actually, it promotes for the conductive, the accumulated benefit of being conductive spacers and promoting mixing. It gives better performance than the graphite current collectors. What we also saw, which was quite surprising for us in the beginning, was that this current increased with time, and it increased only for the 3D printed gasket. So when we opened the stacks, actually what we saw that some part of the YP50F carbon actually penetrated inside the 3D printed materials. And so basically we believe that it added some extra conductivity along time as the carbon penetrated into the 3D printed structure and decrease along the time the resistance of those 3D printed gaskets. And indeed, we measure the resistivity of the materials before and after use. And indeed, for 3D printed materials, it's decreased. For graphite plates, it keeps the same. So the answer to the question, to the initial question, is yes, at least in our opinion. And it's actually, we think also that 3D printing has several advantages because it was very easy to use. It's very available. Anybody, it's much more available than CNC milling. So it opens possibility to researchers from almost everywhere could study FCDI processes. And also there is some advantage because 3D printing generates less waste than CNC milling, because CNC milling is a subtractive manufacturing. So everybody who already worked with CNC milling, you know how much waste and dust it generates. So this is one of the advantages of 3D printing. It's much more cleaner. Also, there are some potential future advantages of 3D printing. For example, CNC milling only allows you to create very simple geometries. Usually in all presentations which I saw so far, it was always with serpentine channel. But with 3D printing, you can create much more complex geometries. And therefore, even furthermore, increase the mixing of a flow electrode. Finally, you can try different materials. For example, what we used was PLA with carbon black, but obviously it was the first attempt. So if you have a filament extruder, basically you can prepare your own materials by mixing different materials, adding different content of carbon black or other conductive materials, and basically to make your own filaments. So I hope that you agree with me that it's possible to replace the graphite current collected by 3D printed materials. And I would like to thank you for your attention.
Presentation, and also we can have 1 or 2 questions from audience, or all right?